Okay, question 5. A spherical oil droplet is located between the plates of a parallel plate capacitor. The plates of the capacitor are horizontal. So let's say if there's one plate here, the other plate is like this. The charge of the oil drop is 1.0 E. So there's a oil drop here somewhere, and it is in equilibrium. Okay, so that's important. If the voltage across the capacitor is 500 volts, so if the capacitor is like this, then VAB is equals to 500 volts. Charge on the drop is 1 E, or 1.6 times 10 to the minus 19 coulombs, and the distance between the plate, let's say if this is D, so distance D is 0.5 centimeter, which is the same as 0.5 times 10 to the minus 2 meters. Now it says we need to find the radius of the droplet, and density is given. So let's say density is rho, so it's given to us 0.9 times 10 to the 13 kg per meter cube. So it's already in SI, so you don't have to convert that into SI. And there's this charge. Let's say this is the charge we have here. Okay, it's the charge here. The important point here is this charge is in equilibrium. Okay, I mean, so when you see equilibrium, you should think of balancing the forces. And this is a classic example where they are trying to connect what you have already seen in 231 with 232. So because this is a vertical setup, right? So this guy Q, it has some mass, let's say M. Okay, and you have seen in 231, and if you haven't, just don't worry, but think of this: if it is in equilibrium, that means that there will be balance of forces, right? And we all know that in a parallel plate capacitor, there are electric fields like that, right? And because there's a charge in the electric field, there will be some force on it. Okay, so if I make that guy here, there will be some force on it that will be pushing it up, electric force, and there will be another force pulling it down, that will be the gravitational pull. And because this oil drop is in equilibrium, we have this going on. Or because Fe is same as charge times the electric field, I have charge times the electric field equals to Fg is going to be just mass times gravitational constant. It's going to be mg. Right. Now, electric field is not given to us, but what is given to us is the potential difference across the plate and the distance between the plate. That means that using the fact that you can write electric field as change in potential over distance, or dV over dx, electric field is going to be del V is 500 volts, and the distance is 0.5 times 10 to the minus 2. So it was easy for me to see this because I had already written down these things here, what is given to me, right? I know the distance, I know the density, such things. I have also made a diagram here. So initially, when you're starting to do a problem like this, it's important to make diagrams, label them, write down the things that are given to you and the thing that is required in the question. So we can just replace that E here, and it will be charge. I'm solving this equation now. Charge times 500 over 0.5 times 10 to the minus 2, then mass times 9.8, right? So at this point, you should not worry about what mass is, because density is given to you first, and then density in any system, like this is a definition of density, is mass per unit volume, right? So I can replace, let's replace Q. So Q is 1.6 times 10 to the minus 19 times 500 divided by 0.5 times minus 2, and mass is going to be density times volume. Let's call that volume V. So it's going to be density times V times 9.8. See, we needed to find the radius of this droplet, right? In the very first look of the question, it is difficult to understand what we are supposed to do, how we'll get to the radius. But see, we started looking for the hints, and the number one hint that we should look for in this kind of problem is that this thing is in equilibrium. So why is that thing in equilibrium? Because there's electric force that is balancing the gravitational pull. Once you write that down, then you are able to see more things, like density is given to you. Okay, how do I get density? How do I get radius from density? Well, if you write this as density times volume, which we have written here, you can replace this volume. So this is a side calculation we are doing. Because it's a spherical drop, see, everything is given to you. It's a spherical drop. Nice. So because it's a spherical drop, volume is going to be 4 over 3 pi radius cubed. So that means I can replace that volume V with the formula 4 over 3 pi r cube, and density is given to us also, and density is 0.9 times 10 to the 13. So I'm gonna put all the values in the end. Oops. 10 to the minus 19 times 500 times 0.5 times 10 to the minus 2, 0.9 times 10 to the 13. That's a large density. 4 over 3 pi r cube times 9.8. Now all you have to do is solve for r cube. So you bring everything here. That means you'll have 1.6 times 10 to the minus 19 times 500 divided by 0.9 times 10 to the 13 times 4 times pi times 9.8. The numerator you have 3. That is equal to r cube. 1.6 times 10 to the minus 19 times 500 times 3 divided by 0.9 times 4 times pi times 10 to the minus 19. Okay, so you just solve for r. So you'll get that r is going to be around 76 times 10 to the minus 6 meters, or 76 micrometers. And that is your answer. Question 6. So this is the last topic you have in your in the chapter of VV. Let me make sure that this is the last topic we have here. Yeah, this is the last topic for the chapter, and it is about dipoles, right? So a dipole is basically a system of two charges, where one charge is plus q and one second charge is minus q. Yeah. So to solve this problem, you need to understand that, look, think about it. If there's electric field here, right? Some electric field, let's call this A. The positive charge here, this guy, is going to feel a pull in this direction, right? And this negative charge is going to feel a pull in this direction. So this dipole, a system of two charges plus q minus q, has a tendency to rotate. Now that rotation will be in such a way that it will align, the dipole will align itself with the direction of electric field. So it's very much as like if I'm lifting a pen from a desk, right, up to some height. If I let it go, it's gonna fall. So there's like a equilibrium position of the system where this dipole really wants to align with this electric field. So if I do anything that resists that alignment, that natural tendency of this dipole to align itself with the electric field, that will give energy to the system in terms of potential energy. So if you want to see an analogy, if you want to think of an analogy, just think this guy, like if I pick up a ball from a desk, right, I'm trying to disturb the equilibrium. Equilibrium is when the ball really want to be on the desk. So if I need to do work on that ball in order to disturb the equilibrium. So in a similar sense, and you can look in your book, there's a potential energy associated with dipole in the electric field, and that potential energy is given by U, and that is minus P dot E, where P is the dipole moment, and it's a vector. To be precise, in your book it is defined as P equals Q, whatever charge is on the positive end of this two charge system, times the distance, and it is defined as 2a, but it can be anything, Q times just this distance we're talking about, right? Now this was the theoretical background of what we will be doing in this problem. But the problem is basically there are not A, but there are 10 to the 21 water molecules. They have dipole moment to be this. So let's write that down. So dipole moment, now I'm solving the problem. So dipole moment is 6.3 times 10 to the minus 30 coulomb meter. So I took a pause there because I thought it's just coulombs, and that can't be case, because dipole moment is charge times distance, so it has to be coulombs times meters. Okay, so a sample contains 10 to the 21. Let's say I'm going to call that number capital N, and it's 10 to the 21 water molecules. So initially, so this was all related to the problem, but not directly what we will be needing in the problem. So I'm going to make a diagram now. So that the condition now is that initially the dipole moments, okay, let's think of just one water molecule for now. For now, just think of one water molecule. So initially we have this. If you have electric field like so, right, then dipole moment was aligned. So that means, and the direction of the dipole moment is the direction of a vector from minus q to plus q. So this is what's happening. This dipole moment is like this. This is plus q, and this guy is minus q. So that is the direction of the dipole moment. So then this is the electric field. So it is aligned with the electric field, right? And electric field magnitude is given, that is 2.5 times 10 to the 5 Newton per coulomb. How much work is required to rotate the dipoles from this orientation, this is theta equals to 0 orientation, to one in which all the moments are perpendicular to the field? So I'm just talking about one moment right now, one water molecule moment. So this is the final condition, 90 degrees. And this is our dipole here. Just going to make an arrow to know that that is the dipole, but it's really like this. If there's an arrow like that of dipole moment, it is plus q and then minus q, like that. This is the same thing. So see, as I said, this system has a tendency to align itself. The dipole has a tendency to align itself with the direction of the electric field. Now if I try to disturb that alignment, that will be as if I'm trying to lift a marker from the desk. Okay, I will have to do some work on it. And if you remember the work, if I let go at this position, definitely this guy is going to rotate back, and it's going to rotate back to the, and it's going to make its direction align with the electric field. So the work done is given by the change in potential energy. In our case, change will be U when theta equals to 90 degree, minus u when theta equals to 0 degrees, right? And then u is given by minus p dot e, so it's minus p dot e, and this will be minus again p dot e, but this is theta equals to 0 and this is theta equals to 90 degree. This will be just minus magnitude p, magnitude of electric field, times cosine of 90 degrees, minus plus this p times e cosine of 0 degrees. So cosine of 90 is 0, so just have p times e, and cos 0 is 1. So this is the work done required, and this is for one molecule. Remember, I'm just talking about one molecule for now. So for to turn one molecule 90 degrees from its orientation, if the orientation is theta equals to 0 degrees, you need to do this much amount of work, and p and e are given to us, so you don't have to worry about them. You know the values, right? Now to do the total work in each of these molecules, and there are 10 to the 21 molecules, you just do this. Total equals to number of the molecules times p times e. For 1 multiplied by n number, it's going to give you total work done, and if you plug in the numbers, it's going to be 10 to the 21. P is 6.3 times 10 to the minus 30. Make sure that everything is in SI. And E is 2.5 times 10 to the 5. And if you do the numbers, you'll get not net, but this is total. So it's total is equals to 1.6 times 10 to the power minus 5 joules. That's your final answer.